can come back and do. Or anything related to what I have said. I'm happy to answer, or anything else in nonlinear systems that you want to ask.
Yes. After some question we can take.
Sure, sure. Yeah, go ahead. Yes.
So what would happen with multiple inputs?
Multiple inputs is a little bit more complicated. I can give you the source, but for a first, in 2 lectures, giving multiple inputs is a little bit. So you have multiple inputs, multiple outputs, then you want to make the relative degree in terms of the summation of the relative degrees. So the exact procedure, the same procedure is there. Are you familiar with Isidori's book? Multivariable, not multivariable, nonlinear control, I think. It's there in that. Just the next chapter.
So this is for only single system.
I have done it for a single input, and I have assumed that I have one output. Yes. So I would call it single input output feedback linearization. But this can also be generalized to the multiple input, multiple.
Scalar, yeah.
U is a scalar. You're right. Yeah.
When we have this multiple output, this rank contribution is that things. How we'll make the whole matrix?
Yeah, and also the relative degree between inputs and outputs. Huh.
Shorthand notation.
Huh.
I don't see it as being any special advantage. The notation is.
Okay.
That is, it seems as heavy as the previous one. In fact, the
Previous one, there is no notation, I think, right?
It's not notation, but
Ah.
so direct. This way you can memorize the notation, what it means. But it is, as a mnemonic, it is not serving a
But you probably must understand that this mnemonic proves very useful when you because engineers have just borrowed from mathematicians' theory in some sense, all these things, right? I mean, so when you do multiple vector fields, this has a nice way of, just like the Lie bracket, you might say, why not write it? I'll show you the expression for it. For instance, if you write it in coordinates, the Lie bracket, just as you made a comment on the Lie derivative, let's say f and g are vector fields. The Lie bracket of these, which is a vector field, in coordinates it's given this way. This being an n by n matrix minus it may be nice looking at it like this, but as you do more involved math with that, it's nicer to carry along this symbol. Same way, your question, instead of writing this, why not write this, right? It's easier to carry along this. For instance, when I keep doing this with, this is much easier when I take left operations by Lie derivatives rather than writing this all over. Okay, so we have landed up in this form. So now let us do, having got this set of transformed coordinates and got our system in this transformed coordinate set, we will do the following. We will define Is this big enough? So here is my new control. And what permits me to write this? What permits me to write this? Because remember, this is non-zero. This is non-zero, right? So I write. So if I put this there in this equation, what happens? Yes, you will just get V. So you will have the first subsystem. So I'll call this subsystem from now on these variables. I'll call them as psi, and these variables I'll call them as eta. Okay. All right, so then I get do you all agree that this is a linear system? A linear system of order k, right? And the rest is this is your order system. Right? So what have we done? By using an input of this form, we have cancelled k of the state nonlinearities and rendered k of the states linear, whereas the remaining are still nonlinear. So we have, through active choice of the input variable, rendered part of the system linear, the other is still nonlinear. So that's why it's called feedback linearization. That is, you're actively using feedback to linearize your system. And now when you have this system is, I can erase this, right? So that, as you see, I said I'd call them psi, so it's psi dot equals and then eta dot, the rest of the variables is, I'll call it use some other symbol, maybe I'll call it m. M is the same, what did I use here? Yeah, I'll use m. Why psi and eta? Because here I have all the variables. I mean, I don't really have. So this is now your system. Your original nonlinear system through feedback linearization has been converted to this new system, which is partially linear, partially nonlinear. And you still can design this. Because all that you did was you specified the earlier u in terms of a new input and a part which cancelled the nonlinearity.
We have to still talk about constructions of psi.
Construction.
Construction of psi function.
Oh yes, yes.
We are still not talking.
These functions, right? Yeah, yeah. More than that, I think I have to talk about when all this is possible also. Yeah. Okay. All right. So at this stage, yes. Let me see what's the best. Okay, just to complete a few, something which is all right. Suppose k was of the order n. That is, if you yes.
I got a quick
Yeah.
comment or clarification. Whatever.
Yeah.
Why do you have to really assume that control fellow doesn't appear in the rest of the thing? It can still appear rest of the eta dot thing.
Yes, yes. This is one form of it.
Control can still appear there.
Well, it does. It does appear because it's affected by psi.
It can still appear.
Yeah, if you choose your psi differently, it can directly appear too. These are called the normal forms where you have the Lg psi I equals 0. Yes, it can. Remember, this form I have written is under the restriction, or rather I have made the restriction on the psi's that Lg psi i's are 0, right? So that gets rid of the additional u, right? Or the appearance of u explicitly. Though this does get affected by u through this, right? There is this. Okay. Now there's a notion called what I was saying just before this question was, if k was equal to n, then this entire thing is a linear system and you just have linear feedback. I mean, you can use linear feedback to stabilize this. So there's a notion associated. So I picked out a couple of topics. As I said, it's not a comprehensive lecture, called zero dynamics. And why is this important? So zero dynamics. Okay. Suppose I have a system in which I zero the output. Let's say I'll give you the reference pages where a nice DC motor example has been solved, where you want to control the speed at a certain velocity. Since it's a third order system, writing down things is going to be difficult, but the example has been solved in Isidori's book, so it goes exactly the same way. So suppose in a system you have defined the output as a desired output value minus the actual value. So ideally you would want this variable to go to 0. That is, you want the actual value to be approaching your desired value. So in that case, you zero your output, that is your h of x becomes identically 0. The output goes to 0. Now, if the output goes to 0, you have to check about a few things. Can you tell me, if the output goes to 0, what is the implication in terms of these variables here? What was this h of x was psi 1? Remember, psi 1 was that, right? So what does this mean? If through some choice of my input I made the output go to 0, then I would have the following. This is 0. So what can I say about psi 2? I know psi 2 dot, oh sorry, psi 1. Psi 1 dot is psi 2, then what is psi 3 and so on. So I'm saying through an appropriate choice of my input, which I don't know whether I have the explicit expression, I make my output, so the first variable go to 0. You can work it out yourself. That will result in all the psi's going to 0. Psi 1, psi 2, psi 3, psi 4 to psi k going to 0. So what you will be left with is a system like this. So all the psi's going to 0, and then this part, which is eta dot, is some nonlinear function of 0 and eta, because the psi's are 0. The reason this is called zero dynamics is because you're outputting, you're zeroing the output. Once you zero the output, there is a part of the dynamics which is hidden. Note here that eta is getting affected. You don't want the eta variables to get large. In any dynamical system, you may have your objective as certain part of the system behaving as you want, but at the same time you don't want the other variables of your system to get unbounded, right? So one has to check that these dynamics are stable. So these are called the zero dynamics. And you need to make the zero dynamics stable. Is that understood? Right? So because that's the part of the system you're not seeing through the output. Okay? All right. So now let me do. Okay. There was one, there are a couple of things which I sort of have to fill in the loopholes here. So I made the following statement. I asked you to accept during this process of coming till here. I said, once again we'll keep all things fixed, k relative degree less than equal to n. We'll keep that, right? So I asked you to accept that these coordinates are linearly independent. So for that purpose I said that we assume because that they are linearly independent means the following, that this K by n matrix had rank K at all points x in the region we were looking at. How do we show this? How do we show that these K row vectors are in fact linearly independent at every x that we are examining? So we show it as follows. is what we are trying to show clear? I mean, you should be. Remember, during the process of my derivation, I had made this assumption, right? So I have not shown it. So it's a sorry. D means the gradient, dou h by dou x1 dou h. So this is. This, the gradient if in Rn. Okay. So this. Okay, so now the way I'm going to do it is sort of slightly different. So, okay, let me start here. G. This is where I require defining all leaf brackets. Now, as we see how we will get output. See, because what have I done through this entire exercise? I've given you a nonlinear system. I've said we have this output of relative degree so much. The question which would naturally come to you even in this restricted single input, single output case is, suppose I'm given a nonlinear system. Can I choose some output through which I can render full state feedback linearization? Is there a particular output in my system? Maybe that is not a feasible output in terms of the physics or the engineering, but still for the mathematical model given, can I get such an output, right? So let's now first answer the question and then go there. So this is a column, leaf bracket of f and g, everything, all notation is the same. So this will be to see this, we'll take a particular small case. Okay. The way I'm going to show that k of these vectors, they form a linearly independent set, is I'm going to do the following. I'm going to multiply this k by n matrix with a k columns, and so product of these two is k by k. What are these quantities? Vector field G, leaf bracket f and g, again a vector field, leaf bracket f with fg, then f with ffg, so on till I have k minus 1 such brackets. Is that clear? So if I multiply this with this matrix, I get a k by k matrix. Does everybody agree? And if I show that this k by k matrix has a non-zero determinant value, if this k by k matrix I show has a non-zero value for its determinant, square matrix, right, I can take a determinant, then what does it imply about these two? That both of them have rank k. Because if their rank was less than k, this determinant will be 0. You multiply two matrices, the product has a rank which is the minimum of the rank of the two matrices. Is that result clear? when you multiply two matrices, the product that you get has a rank which is the minimum of the rank of the two matrices, correct? So, I will go to show that this multiplication yields a matrix which has a non-zero determinant and therefore has rank k. Is the logic of my procedure clear? Right? Okay. Now, this looks very intimidating. I mean, it looks so huge and it looks like we get scared of it. So, let us do it for a 3 by 3 matrix case, so you do not have to keep track of this, right. Okay, so 3 by 3. So I will assume that okay, I have. So let me write these things clearly. To show this, you can show the general case, but I'll assume n equals 3, k equals 2. Okay, n equals 3, k equals 2. Therefore, I have dh there, then I have d LFHX, correct. So, this is 2 by 3, correct. Here I have G and actually this case may turn out to be very simple. Okay, anyway, let us do it. So, k minus 1. So, 2 minus 1, 1 bracket, correct. K minus 1, k I have said is 2. I am taking a nonlinear system, order 3, relative degree of that output was 2. 2 minus 1, 1 leaf bracket, right. So, this is 3 by 2. So, what does the product of this yield? This yields a 2 by 2 matrix which looks like this. Now that you have gained some familiarity with Lie derivatives, how will I write that matrix? Because it is going to be full of Lie derivatives, and how much ever you want to stay away from them, you will have to use them. So, the first, this by this will be what? Lie derivative along the vector field Fg of H, correct. This by this will be what? This by this. Now, please tell me, can I say that the determinant of that 2 by 2 matrix is non-zero under these assumptions? First and foremost, you will think that all this is a function of x. Yes, they are functions of x, but you are evaluating at each x in that region in which you are following this procedure, right. So, let us see. What about this term LGH? Is it 0, non-zero? think. This means what? Let's write down. So let's make a demarcation here, and okay. This means what? LG H equals 0 and LG F H equals 0, correct? Relative degree 2. These two are true. Therefore, we can directly say this is 0. What about this term and this term? What about this? Now that's a little bit confusing because I have not shown you so far, but in Lie derivatives, the Lie derivative of this, that is along this vector field, is you can prove this, actually you can prove this. That is, this basically means you take the Lie derivative along f, then along g. What is the difference between doing along g and then f? Because the whole idea of this Lie bracket is it's a commutator. In mathematics, it starts from the fact that how close are you to commuting? See, when I take square matrices, let's take the Lie bracket on, say, matrices. When I define Lie bracket of two, so I'm just going on the side. Let's say I take A and B are n by n matrices. Then I will define the Lie bracket AB minus BA. If the Lie bracket is 0, it means these two commute, right? The Lie bracket is a measure of how far from commutativity are your two quantities. Like for example, in the coin problem, in the wheel problem I explained, you rolled, steered, rolled, steered. Now if those actions, those vector fields commuted, you will get back to the same place. You would never have moved. It was the measure of non-commutativity which allowed you to have that translation. Is that point clear? So the Lie bracket is a measure of that non-commutativity. So okay, let's take this. Now please get back to this answer. So what is this? So let me write this down. So this is this. Out of this, which is everything 0 here for this case? I can definitely say this is 0, correct? Ram Prasad, right? Is that, do you see that? This goes to 0, but can I say this of the other term? The other term is non-zero. Oh, sorry, did I do it the other way around? No, it's fine. LF, no. The other term is not 0.
Not 0, not necessarily 0.
Not necessarily 0, yes. I think you can show that it is not 0. I'm trying to recall how you will actually show it. It is not 0 because of all right, the fact that if it became 0, then your f and g are commuting vector fields. Therefore, everything goes to 0. This will also go to 0, and therefore this whole thing will imply, oh yes, so in a sense it would imply the Lie bracket of f and g goes to 0, which would imply what would it imply? It would I think it has to necessarily be non-zero. I'm sorry, I'm not able to recall exactly, but I'll think about that. But okay, let's say we cannot conclude this is 0 right away, right? Is that seen? I mean, is that, yes. Is this? This is from here because of this, right?
Yes, yes, when both are there, then both the right hand sides are 0, 0, that will be 0. Definitely.
Which one? If this is 0?
Matrix,
Huh.
we have got already 1 by 2 element is 0, 2 by 2 element is also 0.
2 by 2, 1 second, have I made a mistake? 2 by 2, 1 second, I think, yeah, I seem to have made some mistake here. GFG DLF. Oh yes, yes, I think I have. This is, if it's relative degree k, this is not 0. K equals 2, that's not 0. My mistake is, if it's relative degree 2, how can this be 0, right? Because wait, I've got to work this out carefully. So relative degree k means no, maybe hold on. I got so the first differentiation is 0, right? But the second will not be, because second will yield the input. So that's wrong. What I wrote here is not correct. Please note, I wrote this here. If I am assuming relative degree k equals 2, this is not correct. Yes? So this is not correct. Do you see that? That's a mistake. Because when you differentiate twice, the input does appear. So that cannot go. Okay, so people are not convinced, so right, let's do it. Correct? Y equals hx. This is 0, correct? Relative degree 2 means at the next stage I should have the input. Agree? So this is not 0. Does everybody see it now? Does everybody see it? So this was wrong, what I wrote. So this is okay, this is fine. So as he pointed out, this is not equal to 0. I'm sorry. So that's not correct.
That's good.
Yeah.
That's a diagonal element. It better not be 0.
Yeah, yeah. So this is not equal to 0. So the commutator, actually that's the leave along the, this going to 0 would mean bracket f and g would go to 0, and that's not permissible. So I'm trying to think what is the condition why that will not occur, but you will have to maybe take that much for this. This is definitely 0. So you have this non-zero, and therefore this determinant would be this into this.
Because other thing is 0 anyway.
Yes, so it's just the product. So in the 2 by 2 case, you can see it. But what happens in this case? So that was the 2 by 2 case. So what will that expression look like? Is this okay?
But that still doesn't remain that, I mean, it's not necessarily 0. It can also become 0.
No, that will not happen. There is a reason. Probably I'll just think about it. Why the commutator? Because this going to 0 would mean something in terms of one of the other procedures that we have done. And
Probably that will violate the invertibility. That inverse properties of the
I'm trying.
transformation is invertible, right? That will violate property.
Transformation is invertible. I'll have to give that a thought. So let me just come here. Oh, sorry, I shouldn't have erased this. So this is what you were looking at. Okay, so in the case, so you'll get a k by k, which I'll just write a few expressions to show you. So this essentially will also turn out to be a matrix like this with zeros here, and therefore you have the product of these diagonal elements, which you can show are non-zero, and therefore conclude that this matrix has rank k. So maybe I will not go through it in detail. For the 2 by 2 case, I've sketched it out, though there is one technical point which he's pointed out, so which I'll try to.
LFLG is not 0. LFLG of H.
Huh.
If that is not 0, then fine. The proof is there. LG LF is H is 0 anyway. And the bracket you have expanded, no? The one term in the bracket of the first term, one term is 0 already. The second term into second term, that becomes square of the term.
But I thought we just said LG LF is not is non-zero, right?
LG LF is 0. But LF LG is not 0.
No, but I thought that was the mistake we made earlier. By relative degrees, I think it's only LG H should be 0, not the other one. LG. Okay, so essentially, yes. Yeah, just LGH, correct. So let's leave it at this. Now let's answer a few other questions related to this, which is the following. So the question is, if you are given question, given under what conditions could we find an output y, let's say, is some lambda x such that in a region U containing x naught, the nonlinear system is input output feedback linearization, is completely okay. Feedback so does everybody realize why this question is being asked? All throughout now we have assumed we have an output of some relative degree. So just given a nonlinear system, when can you find some output? It could be anything, but as I said, this is just a mathematical question. When can you find an output such that the system is completely feedback linearizable? Right? Okay. That is k equals n. K equals n. So not k is not strictly less than n. So it's not that part of the system is linearized. Yeah?
Input to state linearization.
It's input to state, is it? The terminology? Is it? I thought it was, it's not input out. Oh, okay.
I have one question. What is this difference they use, the feedback linearization and the dynamic inversion? So that's same only or terminology? Or?
You'll have to just tell me exactly. In dynamic inversion, you are inverting the entire plant, right? And cancelling all the nonlinearity.
It also works on output. You choose some output for output.
But I thought it's almost the same. That is.
My understanding
yeah.
is the feedback generation. You leave it as a linear form. You don't design a controller. Right? Feedback dynamic inversion end up designing a controller also depending on your objective. Right?
But they are equivalent.
See, you're not designing that V. You're leaving that V as it is, right?
But in dynamic inversion, is it
end up designing a V also.
Okay, all right.
But V you are leaving, but
you could design. I mean, it's
that's the linear form you have given.
Yeah,
right?
linear form I've given.
Only that linear form it's just V equal to minus kx for step.
That's fine. That's fine. Yeah, that's all. Because linear
So
design.
we just have to write one more step equal to.
Yes, if that's what it is. But I'm not very familiar with this, so you are the expert. So you have. Yeah.
So we'll leave it there. I mean, let's not confuse.
Okay. All right. Yes. So does everybody else follow the importance of this question? That should be clear. That given a nonlinear dynamical system, can you conclude that? So for this, so in fact, your question, Ram Prasad, about why we need Lie derivatives and Lie brackets, when you come here, it becomes just impossible not to use them, because you have a notion called integrability, and I think that gets very difficult for an nth order system without using this notation or these ideas. Yes.
So this U is different from the U which we have used previously.
That's a region. It's not a control.
Oh yeah, I think as
I don't really like that.
yes. This.
Confusing.
Sorry for the confusion. This is.
Previously also we had used U as a subset of R.
Yes.
Defining the system. In the board of we defined the whole system.
Okay, the idea is this. you have Rn,
Read the domain.
you have Rn. As I said at the beginning of my lecture, in linear dynamical systems, everything is defined on Rn. In nonlinear systems, you define things over a smaller set, because usually you cannot make global conclusions. You make conclusions in a region, right? That's why. That's why, to be sort of more precise, I keep carrying the U, but I agree with you. He's also pointed out this U with the small u is confusing.
I was not talking about this U and the small u.
Okay.
Talking about because last time you showed there was no U and then you defined the display of the controller for a region around x naught.
Yeah. What I meant, okay, you can take that small region as U around x naught. Yeah. What you are saying is I had talked of x naught and whether you could feedback linearize it in a small region. Okay, that's once again, I mean, you can consider whether I can do it in U, the feedback linearization procedure. Right? That's okay. Yes. So this can be done. That is, you can find this if the following conditions are satisfied.
Why do we care for the x naught? Is it initial state or is it something?
No, it's because you're doing all these operations in a region around this, and since they are smooth functions, you don't assume that things suddenly change, and therefore you could have regions where your relative degree could be different. I mean, there are some examples, I have not worked it out, like in certain regions your relative degree may be k, other regions it could be k plus 1, k minus 1, because all these are dependent on x, right? So in that sense, so that's why we talk of in a region around. So let's call this 1. Is it okay if I write here? Not visible? Okay. Till here it's okay.
This concept of leaf brackets.
1 second, let me just write this down. I'll just. Okay, I've gotten a new word here which I'll have to explain. Please ask me your question, then I'll explain that. Yeah.
This lead brackets in the development of the feedback linearization procedure itself, we did not use lead brackets. We used it later to prove the full rankness of something.
Correct, yeah. And in this condition.
Oh, yeah.
In this condition, yes. Yes. So, I asked one question, and the conditions which are both necessary and sufficient for that to happen, for you to have an output lambda or output y, what you call it, are that the rank of this vector fields g, f, g, f, f, g, etc. at every point in that region should be n. There are n vector fields, right? 1, 2, 3, 4 to n, right? And this, so the word distribution I have not explained, I will explain. So, the difference between this set and this is I have removed one guy. This n minus 1 is not, this is n minus 2. So, now I am saying that this which I call a distribution should be an involutive distribution.
The first one is a matrix, the second one is a set of vectors.
You can look at either way. Each of these
The rank of a matrix
is a vector, right? Therefore, you can look at it as a rank of a matrix. So, this you can just look as a set of set of vector fields which have to be, it should be an involutive distribution, or first let me write the condition and then explain what this means. It means that you should be able to find a function. This is like your desired output that you want to find, such that let us call this whole matrix C. D lambda this is now a row vector equals 0. I agree at this stage things really shoot up in terms of the complexity, but I thought a lecture on feedback linearization, since I am doing only single input, single input and single output in some sense, will not be complete if I don't give these conditions, right. So, now let us understand what is the meaning of this involutive distribution. I have said that if you do this, so what this means is, this is a condition called integrability of the distribution. This, if you can find a lambda which satisfies this. But first let us go step by step. What is a distribution? So, all of you have done linear algebra. In linear algebra you encountered a notion called subspace. Is there anybody here who does not know what is a subspace? Right? So, if you take this room, let us say we are in R3 and let us say this is the origin. So, I could take the whole floor extending outside and behind me as a subspace, right. So, or in other words, in R3 the following set the 3 tuple where psi and eta could be any real numbers forms a subspace, correct. Now, you have a similar notion of subspaces which is extended to vector fields in the following sense. Suppose, again everything I am considering in a region U. So, you have two vector fields f1x and f2x. So, each of these at any x is an n by 1 vector. Let us say, so I will draw this U, right. So, let us say I pick some point x1, some point x2, some point x3, etc. Right. Now, at each of those points, these are just two column vectors, agreed? These are just two column vectors if I substitute x, and I can find out what is the span of vectors. Clear, everybody? Span of vectors. Or okay, I can find out what is the rank of, say, at any of those xi's of this matrix. So this is n by 2. I can find out its rank, right? If the rank of this matrix at every x in U is 2, that is, the two vectors are linearly independent everywhere, then this which is now called a distribution has rank 2 over this region. Now, so what does the distribution do? At each point it's assigning a subspace. At each point in, see, at each point of here you have an entire vector space in which you can have vectors, right? You have an Rn, but out of that it's picking a two-dimensional subspace. Now this assignment of a subspace by vector fields constitutes a distribution of vector fields. So it's the notion of subspaces being extended to vector fields. Because vector fields give you vectors at a particular point. Now these vectors can span a subspace. If that assignment of a subspace is called a distribution. Okay. Now, so now you will agree that these are n minus 2 vector fields. So they assign a subspace at every point. So they form a distribution. But now I have something more. It's called, the distribution should be involutive. So that's the final icing on the cake. So what that means is that if you have, okay, let's make it simpler. Let's take this case. Let's have, that's a two-dimensional distribution. Right? Now, suppose the Lie bracket of F1 and F2 could be written as just a linear combination of these, and even further Lie brackets could be written as linear combinations of these two vector fields. Then that distribution has a special property. It's called an involutive distribution. That means what it says is, no matter how many Lie brackets you take of these vector fields, the resulting vector field that you get is just in the span of these vector fields, or can be written as a linear combination. That's called an involutive distribution. Now, what makes it difficult to check something is involutive? Because if I just ask you to check this for two vector fields, it's very difficult. How many Lie brackets will you keep taking and check whether it can be written as a linear combination? So there's a powerful theorem which is called the Frobenius theorem, which relates this notion to something called integrability. That is, a distribution is involutive if and only if it is integrable. And integrability is this condition, that instead of finding all Lie brackets, finding out whether they can be written as a linear combination of those vector fields, instead if you come out with a function lambda and you show d lambda times c is 0, that is, this row vector destroys all those column vectors, then this is an integrable distribution and therefore involutive. So to conclude, I have to satisfy these two conditions. So where am I now? 5:30. Okay. So questions so far?
So in the early part you related Lie bracket to cross product, sort of give the intuition of cross product approximately, right? For Lie
Correct,
bracket.
correct. Yeah, but that's
Exactly
not, yeah, it's not exactly, see, because here we're talking of functions. In cross product we don't have a notion of derivative. Here we have to be slightly more careful, but that's a nice way to start thinking of the Lie bracket because it gives you the intuition.
Right, because this involution
Huh.
will not happen if the cross.
Yeah,
if the like-
yeah. That would not happen. That's why I said take it with a pinch of salt. It's not exactly it, but it helps you to think because the cross product of two vectors gives you a vector in a completely new direction. Right? Yes.
So you said that the relative degree is region dependent.
Correct.
It changes according to the
Right.
Why is that?
Because you have those things as functions of x, right? If you have a function, let's say sine of x, close to 0 and pi, it will go off to 0. But in other places it should be fine, right? Suppose in one of those terms where you had LG, LF, H, suppose you had a term which came as sine of x into u, right? Now close to x equals 0 and x equals pi, the u will disappear, right? U has, if u has a function, because it's g of x into u or something else, that suppose you said that, so that one could be, you had something like this, or you had maybe, so at x equals plus or minus 1, this will go off. Okay. Yes.
Then the definition of distribution,
Huh.
does it require to be prudent again?
In this case, it's rank 2, right? It's rank 2, yes. Okay, there are more notions. For example, if its rank falls, it's not called a regular distribution. I mean, so normally in all these problems, we assume it's a regular distribution, so its rank is constant over the entire region. Yeah. So there's one question I think which you said, how to do the LG psi. Maybe I can talk to you about it. So there is,
Work it out and send it across in circulative.
I'll be happy, I'll do that. I'll work out 2 or 3 examples and send it across as a file. And I'll also write up these notes. I've already written most of it, so I just need to typeset it in maybe 2-3 days more. Yeah. Any other questions, nonlinear control? I'll be happy to answer anything what I know of nonlinear control.
That means you have discussed clearly the method of feedback linearization.
Yes.
So from your lecture we have gathered the knowledge, that means for the nonlinear systems which are represented in the space domain, it must be mapped after with the proper transformation, and there are some important operator, or I think Lie bracket and Lie derivatives.
Correct.
These are required so that ultimately we can generate the control signal which is in the linearized form.
Let's not put it that way. We generate a control signal which linearizes the system. Control signal is not in a linear form or anything. You can't say that.
But
The,
ultimately
the system, part of the system or full system becomes linearized.
whenever that is a control term, that is variable is derived from the states of mathematical manipulation from the linearized systems already, then definitely it will be applied to the physical linear system, which that is the physical linear system. So that
No, but, if-
account the linearized systems, it will be easier for the control system designer, so that the linearizing effect, it will ultimately the control systems, control signals will be applied to drive the physical nonlinear systems. Is it,
Okay, there are a couple of things which you said. The control that you apply
yes.
to make your system look linear, that you can't call it a linear control or something like
No,
that.
not with
Yeah,
linear control.
yeah. So you apply a control to get rid of all non-linearities and to make your resultant system look linear, but with still a control left for you to use any of your familiar state feedback, pole placement, any of the techniques to design your control.
Already,
Yeah.
Something called pseudo control. That V is the U is converted to V.
Huh.
In the literature, that's called as pseudo control.
yeah,
The pseudo control variable will be a linear form in the transform coordinate system.
yeah.
Okay, if it is a full state feedback linearization form, like that K is N,
Huh.
then your V will be a complete function of Z. Z contains everything. But then Z you can convert back to X, the phi inverse and all that, and then your actual control signal will be nonlinear form. Because between Z and X there is a nonlinearity. So that will kick in this.
There will be a process of another inversions or like.
You have to do that. I mean, there is no, see, V has no meaning, only U has meaning.
Yes, yeah.
Maybe this,
You might know that. Did you talk about that?
My question has not come to it. So the next step is that is, we know what is pole placement method, because for an unstable system by following the pole placement method, the closed loop system can be made stable.
Correct.
Okay. But whenever this technique has been applied, then whether the poles of the nonlinear system will be altered.
No, there's no notion of a poles of a non-linear system. Poles is a linear system concept. Poles is entirely linear. You can talk of other stability concepts in non-linear system, but the poles you cannot trans. Yeah.
If your system is again completely linearizable,
Huh.
then in the linearized coordinate frame, you can still talk about pole placement.
Yeah, that is
You
okay.
design your V using the pole placement controller for in the coordinates of Z1 to Zn.
But that is in the virtual
Virtual
thing.
control.
It's a, it does not exist at all. Because it's a virtual system.
Right. Because it is difficult to handle nonlinear system, this is a platform. It gives you a transform coordinate frame so that the system appears to be linear. It's not really
So
linear.
that was related to the
See,
virtual
for non-linear
system.
system, you don't have eigenvalue. So,
But still you can have.
No. I think his confusion is that both of them sort of gave points. You have. It's not that things are totally independent here. See, the U is written in terms of the V. So finally, when you design that new V, that's affecting U too, right? Because U is defined. I mean, U comes in that expression. The only thing is, as he calls it, the pseudo system, and with the pseudo variables Z1 through Zn, that appears linear in that form, in the Z form. And your V can be designed using your familiar linear system methods.
So there is no need to analyze that is in terms of the stable pole for the pseudo system. There. Is it necessary?
No, if your system is completely linearizable, you are very lucky. I mean, most of the time will not be. So your K will be strictly less than N. Then you have to worry about zero dynamic stability. Okay, if your zero dynamic is stable, interdynamics are also stable. That's
So
the
that part is not needed for stability analysis.
No, zero dynamic stability analysis you will do. Your kth order virtual system will be ensured by design. Your pole placement and other things will ensure. But you will be still left out with the internal dynamics. That's the way the zero dynamics kicks in. So while designing a controller, you have to sit so parallelly that zero dynamics is stable. Then you are done.
See, I will send a third order DC motor example. Please work it out. That will clarify entirely the doubt you have. When you do that third order system, zero dynamics, the control use, everything. And since it's a third order system, and this example which I sent is also being solved in the book by, okay, somebody asked for references.
It will be better for us to have a e-copy.
Yes, I mean PDF only.
Feedback generation, reoperator.
Sure.
Otherwise, what will happen that with this concept, even we go through this lecture at the current session, but due to the elapsation of the time, it may go out.
Sure.
so see,
Yeah,
you
sure.
the advantage, first thing is sending the PDF, we will distribute. Second is lectures are video recorded. So whatever conversation we have,
Oh, let me do
forget,
that.
next time you can see again
I
visual
am tempted to tell something. That's right.
Huh?
I am tempted to tell something.
Oh, okay.
Can chip in a little bit. Sorry for that.
Yeah, sure.
There will be a time there, right? The typical example, the way I can interpret it like this. I mean, all of you are staying in guest house. Most of you are hostel, right? Yeah, mosquitoes. Mosquitoes there or not there? No.
Today they have arrived, so you have to experience.
I didn't tell that. I don't know whatever. Let's say there is a mosquito which comes in and there is a projector there, which kind of picks up that picture, right? So the mosquito trajectory happens to be somewhat like that. It's flying away, right? How do you kill it? How do you kill? How do you kill a mosquito? Right? Yes or no? All right. Okay, so remember that actually, all right? Now, and then this is actually subspace, right? Mosquito is flying in 3D, we have captured it, put it in 2D, like that. Is this linear or non-linear? Is it linear or non-linear? I mean, you should participate. I mean, our lecture is over. Yes, I mean, this is not my talk actually. Tomorrow you listen. It's a fun example lecture. Is it non-linear? How many of you agree? Okay, agree. Somewhere you have to take a stand, right? Why do you think it's non-linear?
What is non-linear?
Huh?
What?
Why do you think it is non-linear? Because implicitly, I didn't tell you, implicitly you have assumed a coordinate frame.
No, I think Radhakant, the question is what is non-linear? I think the question is
What is
what
non-linear,
what yeah.
Motion of the mosquito or the trajectory or
Yeah.
Trajectory. The trajectory, if you see x1 and x2 plane or xy plane, okay, it happens to be kind of a fields nonlinearity, right? It is certainly not a constant signal, right? Do you interpret it as a constant signal, yes or no? You don't, right?
It follows the curvilinear path.
Right, it is not a constant signal, right? Obviously.
So if you put kinematic trajectory for a mosquito, will it be linear or not? So it's
No, I think the question got deviated.
No, I think no. I think the confusion is what is the linearity being referred to?
That's
What
why
is the
is it a constant
yeah,
signal?
yeah,
Let's say
yeah.
if it is time varying, if you take it as time varying, is it a constant signal? Or if you take coordinate frame as x and y, is it a straight line? Is it not? It doesn't look like a straight line, right? However, I will construct a coordinate frame. Okay. That's my coordinate frame. This is x, this is y. Okay. In that coordinate frame, what happens? Okay.
Quasi-linear.
This happens to be a step input basically, right? Okay. So what your hand is doing is probably one hand is doing that coordinate adjustment, other hand is closing the gap. So the closing the gap fellow is essentially, if you talk about a step input, how easy it is to design a controller. We know all that, right? So you also think about as a step input, it happens to be very nice. We can just design some sort of a controller in this coordinate frame. However, for actual meaning, we need that frame, right? This is our frame. So between this frame, whatever you see is orthogonal coordinate frame, whatever you are comfortable with, and this constructed coordinate frame. Remember that the mosquito flies differently, your coordinate frame different. Every time it becomes different, actually, right? Okay, so the question now is, can you really do this back and forth coordinate transformation? Once you do back and forth coordinate transformation, control design becomes easier. Okay, so that is what the process. He has talked about coordinate transformation. The design part you have to do. Okay, once you design it, you will get in the form of, let's say that this is Z1, Z2, and this is your X1, X2, right? Okay, your X1, X2 to Z1, Z2 transformation is done. You do your V design, okay, whatever V of T, so that this tracking happens or whatever happens in the Z1, Z2 frame, and then come back to X1, X2 by this involuted transformation, right? You have got that equal to phi of x, right? Okay, so your x is nothing but phi inverse of z. Now what happens? Your v minus kz, okay, whatever, minus kz is your linear form, pole placement of the thing, right? And z is nothing but k into phi of x. So, but remember, v, you got v, now you have to get u.
Inversion. But here one point to be noted, I think, even which I will integrate in one question from that means the nonlinear model should be accurately known. Otherwise, there will be
Those concerns are certainly there. Okay, this design method, I mean, this is actually very good thing. I mean, this is a coordinate transformation thing, but design method, when you go there are concerns there.
There's another point also you have to bear in mind. Feedback linearization is not easy.